Let me introduce you to a new type of computational model, a pushdown automaton. A pushdown automaton, or a PDA, is very similar to non-deterministic finite automaton, or NFA, which is augmented by a stack with unbounded memory. This small feature upgrade lets the pushdown automaton to recognize some of the non-regular languages. In terms of descriptive power, pushdown automata are equivalent to context-free grammars. So any language recognized by a pushdown automaton can be generated by a context-free grammar. To prove a language is context-free, you can either come up with a CFG or a context-free grammar that generates it, or a pushdown automaton or PDA that recognizes it, whichever is more intuitive and convenient for you. Without further ado, let me introduce you to the formal definition of a pushdown automaton, which is a 6-tuple. If you observe closely, the definition is very similar to a finite automaton, except for the newly introduced set, the stack alphabet, and the upgraded transition function, which includes the stack alphabet. Let me focus on the transition function here and show you how to interpret it intuitively. This is the transition function of an NFA. When you are at a state and you read a character from input string or an empty string, you would transition to a set of states which belong to the power set of Q. Similarly, when you are in a state in PDA, for a given character from the input string or an empty string, and for a given character at the top of the stack, the PDA will be transitioning to a state and may modify the character on the top of the stack by pushing or popping or leaving the character as is. The best way to build intuition on anything new is by looking at an example. Let me demonstrate to you a pushdown automaton that recognizes the language a to the power n, b to the power n, and here is this 6-tuple that defines it. Looks like we can do this using 4 states, Q1, Q2, Q3, and Q4. Alphabet is A, B. The stack alphabet is A, hash. And the final accept states are Q1 and Q4. The trick is to push the symbol hash into the stack right after we power up the PDA. To visualize this, I'll be drawing the state transition diagram with start state, which should be an accept state because epsilon is in the language. Alright, so right after we power on, there would be nothing on the stack. So let me explain how to interpret the transitions which are in the format A, B, right arrow, C. For the input character A, the stack alphabet changes from B to C. So when I write A, epsilon, right arrow, C, I am pushing the character C onto the stack. What should have been an empty character at the beginning of stack is now character C. If I write A, B, right arrow, epsilon, I am popping the character B from the stack into thin air. Alright, so we write epsilon, right arrow, hash, meaning if the input character is epsilon and stack is empty, we push hash into the stack. So this is the thing that we do right at the beginning when the PDA is powered on, and transition to Q2. Now we want to keep pushing A onto the stack if input character is A, which I've written that way. When we receive character B, we have to pop out an A from the stack and go to Q3, where we will keep popping out A's whenever we see a B. When we see an A again in the input characters, the input string would not be in the language, right? So the PDA goes to a reject state because Q3 does not have a transition for the input character A. So what happens when we get to the last B? The character on stack would be hash. So we end up in the accept state by popping out hash. If the input string has more number of B's than A, the PDA will reject the input string because the accept state Q4 does not have a transition for input character B. There you go, a PDA that recognizes the language A to the power n, B to the power n. This state transition diagram can be visualized as a transition table as well. The transition table has the states as rows and input character and the corresponding stack character as the columns. So Q1 with input epsilon and stack character epsilon goes to Q2 hash. Q2 with input character A and stack character epsilon pushes an A to the stack and loops back to Q2. If Q2 receives input character B, the PDA pops the character A and replaces it with epsilon. You repeat the same with Q3 and Q4 and you arrive at this transition table. Wherever it is left empty, the transition is to empty set phi, where the PDA enters a point of no return, ending up in a reject state.